It's our 16th lecture of Principal Methods and Applications of Nuclear Tracks, and in this lecture, we are going to start our chapter number 5 of book Knoll, which is about ionization chambers. Okay, so what are basically ionization chambers? Ionization chambers basically consisting of a chamber having gas inside. When a particle has to be strike and particles has to penetrate into, so this chamber is so known as the chamber, and once the charged particle come into that chamber, they ionize those particles of that gas. So the particles of that gas which ionized after the charged particles interact with that chamber containing gas inside is known as the ionization chamber. Okay, so let's start with this chapter. Basically, several of the oldest and the most widely used type of radiation detectors are based on the effects produced when a charged particle passes through a gas. Okay, so we have to discuss the most widely type of radiation detectors. For that, we are commonly use this. Okay, ionization chamber, which consists of a charged particle, have to be passed through that gas. Okay, charged particle have to be passed through that gas. Here it is mentioned. So the primary modes of interaction involve ionization and excitation. So two things happen after the interaction of that charged particle to the gas. The one thing should be ionization happens, and the other thing excitation of the gas molecules. Okay, because gas made up of the small molecules. Okay, along the particle track. Although the excited molecules can at times be used to drive an approximate signal, because when they move, when they excite or de-excite, they show some signals to verify in our detectors. So that's why we can verify those in detectors. Okay, as in gas. The majority of gas field detectors are based on sensing the direct ionization created by the passage of the radiation. Mostly we detect the primary ionization. Understood? The detectors that are the topic of the following the three chapters which we already discussed: ion chambers, okay, and proportional counters and gigatubes. We already discussed these topics in previous videos. All drive in somewhat different ways. An electronic output signal that basically gives this all about this will be happen within the gas filling the detectors. Now move on towards the ionization chambers. Basically, ion chambers in principle are the simplest of all gas field detectors. There are many gas field detectors, which you know that the one of them is the ion chamber, proportional counter, and the gigatubes. These are all are the gas field detectors. So ion chamber is principle that are the simplest in the gas field detectors. Okay, because gas consists of ions. Here it is mentioned. You can see. So their normal operation is based on the collection of all the charges created by direct ionization within the gas through the applications of electric field. So you have to apply electric field externally. Okay. As with other detectors like ion chambers, can be operated in current or pulse mode. So ion chamber detector can be work on the principle of current or pulse mode. In common application, ion chamber are used in current mode as DC device. These are basically the applications of ion chamber, which is one of the gas field detector. Okay, although some examples of pulse mode applications will be given at the end of this chapter, we can briefly discuss those. In contrast, there is another chamber which I told you. There is another detector which is the proportional counter and gigatubes. Ion chamber is one of them, and other two are proportional counter and gigatubes that are almost used in pulse modes. Okay, they can also be used for pulse modes. So this term ionization chamber has conventionally comes to be used exclusively for the type of detector in which ion pairs are collected from gas. So this is very important thing. Ion pair has to be collected from these gases because when a charged particle interact with the ions of the gas, they may excite or de-excite and they form ion pairs. Not only ions, they form ion pairs, okay, collectively from gas. And then the corresponding process in solids is collective of the electron hole pairs generate. Definitely, there is some electrons and holes. Both pairs has to be introduced in the semiconductor after the collision of the charged particle with this ionization chamber. Okay. So what we learned, there are three chambers. The one is the proportional counter, the Gigermüller, and the one which we are discussing is the ion chamber, so called as the ionization chamber. So when a gas interact with this gas-filled chamber, they produce ion pairs. Simple as that. Okay. So now move on towards our subtopic number one, which is about the ionization process in gases. So, as a fast charged particle pass through a gas, the types of interaction detailed in chapter number 2 we already discussed, okay, created both excite molecules and ionized molecules along the path. As I told you, as the charged particle comes and pass through the gas, what it should do excite molecules and it should do ionize molecules, and it should ionize molecules along the path which they follow after the interaction. Okay, so after a neutral molecule is ionized, the resulting positive ions and free electrons are called as the ion pairs. Okay, so after a neutral molecule is ionized, because uh, initially our gas is basically neutral, so when a charged particle comes, they ionized our gas, so resulting we get the positive ions, because we learned that we get ion pairs. So if positive ion we get, definitely we get the negative ions, so called as the free electrons, and this comparison is so called as the ion pairs, which is formed if initially our gas is neutral, but when the charged particle comes, they form ion pairs. Understood? Okay, so now move on. Basically, ion can be formed either by direct interaction and incident particles or through a secondary process in which some of the particle energy is first transferred to an energetic electron or delta rays. You know that what are delta rays? Delta rays are basically the secondary energies, the secondary electron that emits. We already discussed about delta rays in our previous videos. So there are two chances of interaction: direct interaction and secondary interaction. Okay, regardless of the details mechanism involved in the particle quantity interact in the total number of the ion pairs created along the track of the radiation. This is how ion pairs produce after the charged particle interact with the gas and form ions. This is the table of values of the energy dissipation of ion pairs. The ions which are produced after the interaction for different gases. These are all gases: argon, helium, hydrogen gas, nitrogen gas. Air is also a gas which is a mixture of nitrogen and hydrogen. You know that. Oxygen gas and methane gas. Okay. So these are for the first ionization potential. First in primary interaction, you can see. Primary interaction it 15.7 watt, 24.5 electron volt, 15.6, 15.5 ev, 12.5 and 14.5. For different gases there is primary ionization is different, but for fast electrons you can see the value is changed. These are the constant values. These are also called as the W values, and the unit of this W value is electron volt per ion pairs, because ions has to be produced. One is the fast electron, which is the negative, which is you can say electron produces, and one is the whole pair, whole produced, because ion pairs is produced. This is for negative, and negative particles produced. This is for positive ion produced. Combination pairs formed, and this is so known as the W value. Okay, so this is the W values as per concerned. Now move on towards the number of ion pairs formed. What are the number of ion pairs that has to be formed? At a minimum, the particle must transfer an amount of energy equals to the ionization energy of the gas molecules. So minimum what energy the particle has to be produced? So at minimum, the particle must transfer an amount of energy equals to the ionization energy of the gas molecule. Because if the coming particle has no enough amount of energy to ionize the gas remains neutral until your incoming particle have no sufficient amount of energy. So the minimum amount of energy that the particle must have and the particle must transfer an amount of energy is equal to the ionization energy of the gas molecule. Okay, so if a gas molecule is, let's suppose we are using argon gas, and let's suppose the ionization energy means to excite electrons of that gas. Ionization energy of argon, let's suppose, is 15.5. If my coming charge particle has not enough amount of energy, is below than 15 of 15.5 or 7, definitely they're not gonna ionize that gas. The particle must have energy greater or equal to the ionization energy of the gas which is inside the chamber. Okay, to permit the ionization process to occur. In most gases of interest for radiation detector, the ionization energy for the least tightly bound shell electron is between 10 and 25 eV. So in most gases, the value is given which is about 10 to 25 electron volts. Basically, in most of the gases of interest for radiation detectors, the ionization energy for the least tightly bound electron shells is between this. So this is for the least tightly bound electrons, or you can say shell. This is for the least energy we must have. If we have energy below than 10 or 20, 10 ev, definitely we are not gonna ionize that gas. So the minimal energy is 10 to 25 evs. Okay. However, there are other mechanisms by which the incident particles may lose energy within the gas that do not create ions. Some is another factor. There is another factor. Some of the incoming particles, or you can say incident particles, sometimes lost their energy, and they have now not a sufficient amount of energy to excite those inside gas ions. So in that scenario, there is also probability that your ion pairs do not create. Example, let's take an example. Example are excitation process. Instead of ionization, there is another process which is the excitation process. So example is R for excitation process in which an electron may be evolved, okay, to a higher bound state in a molecule without being completely removed. So in excitation process, what basically happen? Your electron not gonna ionize, but instead of ionization, what it undergoes to a higher bound state, and it goes to the higher excited state instead of completely removed from that shell. Okay, so understood. Two concepts is one is the ionization and the other is the excitation. So if the amount of incoming particle have must amount of energy greater or equals to the ionization energy of the gas molecule, then definitely your particle has to be produce ion pairs. But if somehow any scenario that your particle lost some of the energy while interacting the gas molecules and not have now enough amount of energy, so the only thing he has to do, he just has to excite that electron to a higher energy state, uh, instead of removing completely from the shell. Okay, therefore the average energy Okay, therefore, the average energy lost by the incident particle per ion pair formed, defined as the W value, is always substantially greater than the ionization energy. So, this is the definition of the W value, which I told you above. What is W value? So, what is W value? W value is basically the average energy lost by the incident particle which has to interact the ionization chamber. So the average energy lost by the incident particle per ion pair formed, defined as the W value. is always substantially greater than the ionization energy. So W value must be ion pairs value because ion pair has to be formed. So the average energy lost, which energy loss after the interaction into the gas, definitely energy has to be lost by the incident particles, and ion pairs have to be formed. So their average energy must be greater than the ionization energy. Okay, ionization energy means the incoming particle ionization energy. So this is so called as the W value. The W value is the principal a function of species of gas involves the type of radiation and its energy. Okay. Empirical observation, however, shows that it is not a strong function of any of these variables, and it is remarkably constant parameter. Basically, telling about the W value, okay, of many gases. Basically, W value is a constant parameter and different for different gases, okay, and different types of radiations. This property of gas is a contract with the behavior of the observed and the semiconductor media discussed later, both of which shows large difference in the amount of signal generated by different type of particles of the same energy. Okay, so some specific data are shown in table 5.1, which I showed you here. This is table 5.1. The data shows different W values. Okay, and a typical value which is between, this is the ionization energy. You can see 25 to 35 electron volts per ion. Sorry, W value, this is around about between 25 to 35. All the W value range you can see is between 25 to 35. Okay, electron volt. Therefore, if your incident particle, let's suppose, having energy of 1 mega electron volt particle, if it is fully stopped within the gas, will create about 3000 ion pairs. This is just an example to show you that if 1 mega electron volt particle has to become and strike, okay, which has the W value, which is 25 to 35 electron volts per pair. So if 1 mega electron volt of coming particle has to be stopped in that gas, so how many ion pairs has to be produced? 30,000 ion pairs should produce. Okay, assuming that W is constant value for a given type of radiations. Okay, which is between 25 to 35 electron volt per ion pairs. The deposited energy will be proportional to the number of ion pairs formed and can be determined if the corresponding measurement of the number of ion pairs is carried out. Okay, so this is all about the number of ion pairs formed. How many number of ion pairs formed? We just check it out. If 1 mega electron volt alpha particle has to become and strike to the that ionization gas chamber, which having the W value range 25 to 35 electron volt per ion, they has to be produced 30,000 ion pairs. Okay. Now move on towards our next subtopic, which is about the Fano factor. What is the Fano factor basically? The Fano factor we have to discuss is a very important in the nuclear physics, or you can say in radiation physics, which is about the Fano factor. What is Fano factor? In addition to the mean number of ion pairs formed. So what is mean number? First of all, you know that what is the mean number? Mean number is basically the sum of all numbers divided by the total number, so you get the mean. So in addition to, if you are finding the mean of the ion pairs and ion pairs which are formed by each incident particle, so the fluctuations in their number of incident particles of the identical energy is also interest. So this is known as the Fano factor. What is Fano factor? Basically, this is the, you can say the definition is this: the fluctuations in the number of incident particles of the incident particle which are coming having the same identical energy, and the fluctuations of that incident particles which having the same energy is known as the Fano factor. Okay, this is very interest uh, to deal with the Fano factor. These fluctuations will set a fundamental limit on the energy resolution that can be achieved in any detector based on the collection of the ions. Okay, so this fluctuation basically set a fundamental limit of the energy resolution of the incident particle. Definitely the fluctuations has to be to basically if there basically fluctuation is a factor you can define the incident particle energy. Okay, if there is less fluctuation between the incident particle, you can say that the particle is coming with low energy. The greater the incident particle fluctuates, the greater the energy it has. Okay, this factor is basically called as the Fano factor. Okay, uh, so the formation of the each ion pairs will be considered as a Poisson process. The total number of ion pairs formed should be therefore be subject to fluctuation characterized by a standard deviation. So after that, the total ion pairs which has to be produced, we can fluctuate that after fluctuation. So we can characterize those total number of ion pairs after production by a standard deviation equals to the square root of the average number of formed. Okay, standard factor, standard deviation, which is basically equals to the square root of the average number formed. So we already discussed in chapter number 4 in previous chapter, many radiation detectors show inherent fluctuation that is less than the predicted by the simplified model. Okay, so we already discussed in previous lectures about this. Okay, so the Fano factor is introduced as an empirical constant. So this is how you can define Fano factor in other terms, like the Fano factor is introduced as an empirical constant by which the predicted variance must be multiplied to give the experimental observed variance. Okay, variance. What is variance? The standard deviations, basically. Understood? The Fano factor is introduced as an empirical constant because this is a factor. So this must be has no unit, means this is a constant factor. So Fano factor is basically an empirical constant by which what we predict the variance must be multiplied to give the experimental observed variance. So after the fluctuations we get, after the total ions pair we get, we have to plot. After plot, we have to observe the variance. And after observing the variance, we must variance must be multiplied to give the experimental observed variance. Variance is basically the distribution of the curve. Okay, we after get. So the Fano factor reflects to some degree the fraction of all the incident particle energy that is converted into the information carrier within the detectors. If the entire energy of the incident radiation were always converted into ion pairs, basically what it say, if the incident particle which has to become and it completely distributed all its energy into the production of the ion pairs, and the same amount of energy were required to form ion pairs, then the number of the pairs produced would be always precisely the same and there would be no statistical fluctuation. So this is very important. So what it says, if the entire energy of the incident radiation were always converted into ion pairs, means if and the incident particle has energy and it converts all the energy, means all its energy it lost after the interaction of the ionization chamber with the gas, and it forms ion pairs. It complete all its energy in the production to produce ion pairs, and the same amount of energy was required to form ion pairs. Okay, and same amount of energy we require to form ion pairs, then the number of the pairs produced would always precisely the same and there would be no statistical fluctuation. So in that scenario, there would be no statistical fluctuation. The fluctuation only happens when there is no total conversion of the entire energy into the ion pair production. So if your complete energy has to be converted into ion pairs, total energy is converted into ion pairs, then there is no statistical fluctuation. Understood? So under these conditions, the Fano factor will be zero for this case. Okay, if all energy converted into ion pairs, then your Fano factor is zero. Okay, the introduction of the Fano factor in the earlier discussion in chapter number 4 also points out the importance of the quantitative statistics when some of the particles' energy is lost to process that no results in the ion pairs. We discussed these things in previous chapter number 4, that when some of the particle energy is lost to processes that do not result in ion pairs, they do not produce in ion pairs. So if only a very small fraction of incident radiation is converted, however, then the ion pair would be formed far apart and with a relative low probability. And if somehow you can say, if ion pair has to be produced and there is low probability of production of the ion pairs, and there would be a good reason to expect that the distribution in their number should be flow Poisson's distribution, then they show a Poisson distribution. In gases, the Fano factor is empirically observed to be less than 1. This is very important. So gases, the Fano factor should be less than 1. Okay, this factor is always less than 1 for the case of gases. Understood? Okay, the Fano factor that significance only when the detector is operated in pulse mode. We therefore postpone further discussion of its magnitude in gases to the following chapter on proportional counter, where pulse mode operation and good energy resolution are most important consideration. So here we are just dropping the Fano factor. So now we are moving our next topic, which is about the diffusion, charge transfer, and their recombination. Diffusion, charge transfer, and recombination. So what is this basically? A charged particle diffused in gases. You know that as, and you also know that as diffuses, the Gaussian peak distribution formed. We already know what is Gaussian peak. Okay, so the neutral atoms, diffusion means to has to be diffused. Okay, charge transfer and recombination. How they diffuse, how charge transfer to other, and how they recombine. So this we have to discuss in this topic. Okay, so let's start. The neutral atoms or molecules of the gas are in constant thermal motion once your gas is inside the chamber. Okay, so this is telling about their characterization of the gas inside that chamber. Okay, so the neutral atoms or molecules of the gas are in constant thermal motion. They are constantly moving, obviously, characterized by a mean free path. Okay, for typical gas under standard condition, and the mean path condition is this: 10 raised to power minus 6 to 10 raised to power minus 8 meters. Positive ions or free electrons are created within the gas, because we know that ion pair has to be created, so the positive ion and the negative ions has to be created within the gas, also take part into the random thermal motion. Also, some of the energy is converted into the increase in the thermal motion of the ion pairs inside the gas. Okay, once your charged particle interact with that gas. Okay, and therefore has some tendency to diffuse away from region, and some of the atoms diffuse from the region of high density, because when your charged particle has to become, they increase the thermal motion. As the thermal motion increases, therefore have some tendency to diffuse away from regions of high density. This diffusion process is much more pronounced for free electrons than for ions, since the average thermal velocity is much greater. Okay, so the average thermal velocity is much greater. We can say, for the case of those diffused uh, ions. Okay, so as the thermal motion increases, the tendency of diffused the tendency of some ions has to be diffused to high density, and this diffusion process basically you can pronounce it for electrons basically, and those for ions which have the average velocity much greater. Definitely those ions which has the greater velocity, they has to be diffused. Okay, once as the thermal motion increases. A point like collision of free electrons will spread about the original point into a Gaussian spatial distribution. So you can see the distribution of those as a Gaussian spatial distribution whose width will increase with time, because the Gaussian peak, the width of this is increased with time. If we let this sigma be the standard deviation, okay, this sigma be the standard deviation, this sign sigma as the standard deviation, and of the distribution as projected onto the arbitrary orthogonal axis xyz either, and time t basically t is basically the time elapsed, and the this factor standard deviation can be calculated by this formula. So this is how you can calculate the standard deviation. So by knowing the value of the diffusion factor, diffusion coefficient, and by knowing the elapsed time, you can easily find this statistical factor, which is this, the standard deviation, which is sigma. So let's suppose if your diffusion coefficient, which is 2 multiplies by 10 to the power minus 6 meter square per second, and your elapsed time is for the diffusion is 1000 seconds, so you can easily calculate the standard deviation, and that should be 0.063 meters. So you can calculate this by yourself. Okay, now move on. The value of the diffusion coefficient d. Okay, so this d is basically the diffusion coefficient. A simple case can be predicted from the kinetic energy of the kinetic gas theory, but in general, a more complex transport model is required to accurately model experimental. So this value should be given for the diffusion coefficient of for different materials, and this can basically can be predicted by the kinetic theory, gas theory. Understood? So of the many types of collision that will normally take place under free electrons, ions, and neutral gas molecules. So you can say of the many types of collision, in many collision that will normally take place between free electrons, ions, and neutral gas molecules. Definitely, there are only three aspects. The collision must be between free electrons or either ions, either positive or negative, or either there are neutral gas molecules. Several that are important in understanding of the behavior of gas field detectors. So let's check out this figure 5.1, which is telling us about the charge transfer collision can occur when this scenarios should happen. So this basically shows some types of interactions of charge species in gas that can influence the behavior of gas field detectors. Okay, in the first four illustrations, the interaction species are on the left, and the product of the interaction are on the right. So these are the right for the products, and on the left the products of the interaction are on the right. So right are the products, and these are the interacting species. These are the interaction species on the left, and on the right is are basically the products which are formed after the interaction. Okay, neutral atoms or molecules are shown as simple circles. So these simple circles are basically neutral atoms, means no charge. Understood? So let's check, when a positive charge is interact with neutral, what happens? Definitely, positive ion has to be introduced in flux into the neutral atom, and it becomes this. Okay, neutral and this. And when this is called as the charge transfer. So you can say when a positive ion interact with the neutral. So what happens? The first, so the positive ion transfer their charge to the neutral. So it becomes neutral and other becomes positive. Understood? So this is one of the interaction. The other interaction is the electron attachment. So if electron has to come with a neutral, what happens? You can see it interact with the neutral and it goes inside. It becomes negative ion. Okay. The other interaction is recombination. So if electron has to be interact with the positive atom, positive ions, so positive negative becomes neutral. So you can say a neutral atom has to be formed. And once your negative ion is interact with a neutral atom having a negative ion inside interact with a positive, so neutral remains neutral, and when this inside negative interact with this positive, it formed a new neutral. So two neutral atoms has to be formed, okay, in recombination process, okay. And in diffusion, what should happen? So electron has to be diffused in many neutral atoms, okay, because in diffusion the velocity has to be increased by the thermal process, as I mentioned you before. Okay, so this is all about the diffusion charge transfer, you can say. Understood? So you can discuss these things. Now these are the formula. Now move on towards this. Okay, so positive ions encounters another neutral gas molecules. In each collision, an electron is transferred from the neutral molecule to an ion, thereby reversing the role of each. This charge transfer is particularly significant in gas interaction. So these gas interactions mainly happen in this ionization chambers. Okay, there will be a tendency to transfer the net positive charge of the gas with the lowest ionization energy because energy is liberated in collision, which leaves species as the positive ions. Understood? The free electron member of the original ion pair also undergo many collisions in the normal diffusions. So free electrons members of the original ion pairs undergo many collisions basically, okay. In some species of gas, there may be a tendency to form negative ions. Mostly in many species of gas, the tendency of negative ions by attachment of free electrons to a gas molecules form more. The negative ions then share many properties with the original positive ions to form ionization process. But with the oppositely electric charge, oxygen is an example of the gas that are readily attach electron so that free electron diffuses in air are rapidly converted to the negative ions. Understood? So the concept of the recombination, what is recombination? As I told you before, collision between the positive ions and free electrons may result in a recombination. As this name stands for, recombination means combination of two things, and because this is so means this is a reverse recycled process, means this is a collision between the positive ions and the free electrons may after results the recombination in which the electron is captured by the positive ions, okay, and return to the state of the charge neutrality, because you know that whenever electron has to be captured with the positive ions, they have to form a neutral charge, okay. So basically collision between positive ions and free electron may result in recombination. Recombination means they form into a state of charge neutrality, okay, in recombination state of charge neutrality. Alternatively, the positive ions may undergo a collision with the negative ion in which the extra electron is transferred to the positive ion and both the ions are neutralized, okay. In either the case, the charge represented by the original pair is lost and cannot contribute further to the single detector based on the collection of the ionization charge. So how you can find basically the recombination rate? There is a factor which is so called as the recombination rate. So how you can find the recombination rate? There is a formula for that. So because the collision frequency is proportional to the product of the concentration of the two species which involve the recombination rate and can be written as dn plus by dt, where n plus is basically the number density of the positive species, which is equals to dn minus by dt, dn minus which is the number density of the negative species. These are equals to minus alpha and the product of both n plus n minus. Okay, n plus n minus. And what is alpha? This alpha is basically the recombination coefficient. Okay, this alpha is basically the recombination coefficient. The recombination coefficient is normally order of magnitude larger between the positive ions and the negative ions. The recombination coefficient, which is this alpha, this is normally order of magnitude larger between the positive ions and the negative ions compared with that between the positive ions and the free electrons. In gases, the rapidly form negative ions through electrons attachment. Virtually all the recombination take place between positive ions and negative ions. Okay, so this is basically a factor which is so called as the recombination factor, and here is the formula to solve this. Okay, both their derivative change with respect to time basically equals to the negative of the recombination factor and their product and plus and minus. Okay, now move on towards next, which is the important factor, and this is called as the charge migration and collision. What is basically charge migration means the motion of charge from one place to another migration movement and correlation, okay. And so first of all, in this we have to study the charge mobility. Okay, so what is charge mobility? So in this scenario you just has to apply an external electric field. So in charge mobility, the only factor is you have to now applying external electric field. So if an external electric field is applied to the region in which ions or electrons exist in the gas, if your electrons or ions exist in the gas and you are applying external electric field, what should happen? The electrostatic forces will turn to move the charges away from their points of origin. So definitely the electrons or ions in that gas has to be deflect due to the electrostatic forces which tends to move the charge inside those gas. Due to that external electric field, those inside gas, ions or electrons has to be deflect or move their original path from the origin, and the net motion consists of a superposition of a random thermal velocity together, and due to that external field the inside velocity of that ions or electrons should increase. Definitely velocity together increase with a net drift velocity. So the velocity of that thermal electron or ions inside that gas, after you apply the external electric field, that velocity is known as the net drift velocity in a given direction. The direction, the field, the electric field in which direction you are applying, the velocity the particles gain after the field apply in either the direction, they move in that direction and known as the net drift velocity. Okay, the net drift velocity for positive ions is the direction of the conventional current, because you know that conventional current always flow from the positive to negative. Okay, whereas the free electrons, your negative ions has to be drift in the opposite directions, means have to be drift into the positive. So in conventional current, your positive ion has to be converted into positive ions has to be drift into the negative, and for the uh, free electrons, your negative ions has to be drift into the positive direction, positive. Okay, this is the formula how you can find the velocity of the drift velocity of the particles after applying the external magnetic field. Okay, so the formula says that drift velocity, which is v, is equals to mu, which is the factor. Okay, and the unit of this mu is basically uh, atm per watt, which is the atomic mass unit, which is the unit of pressure. Basically, this mu is basically the mobility factor. Okay, so you can see. This E sign is basically the electric field strength which you applied externally, and this P is basically the gas pressure which is inside that chamber. So the mobility mu tends to remain freely constant, okay, over a wide range of electric field at gas pressure and does not differ greatly for either positive or negative ions in the same gas. Tabular form of the mobility of the ions in various gases is elaborated below. Typically, values are between 1 and this. So, the value of this mobility mu is a range of 1 and 1.5 into 10 to the power minus 4 minus 4 meter square atomic mass unit per watt atm pressure of unit. Okay, so the value of this mobility mu has a range of between 1 to 1.5. Mostly we take 1.5 into 10 is per minus 4 meter square atm per watt. Okay, watt second. Sorry. Okay, watt second. Second also has to be cancelled. So here you can see four detectors gases of medium atomic number. Therefore, let's suppose if and therefore at 1 atm pressure, a typical electric field of 10 raised to power 10 raised to power 4 watt per meter. If let's suppose if your electric field is this 10 raised to power 4 watt per meter, will results are, let's suppose, drift velocity of 1 meter per second. Okay, so if a velocity is 1 meter per second and electric field is 10 raised to power 4 watt per meter, having the value of the pressure which is between 1 to 1.5. If we take 1.5 into 10 to the minus 4, we get the answer, and the answer is 1.5 atm. If we are taking the value in between, so we are getting the value is 1 atm. Okay, so it depends on the value of the pressure which has to be given. Okay, by most standards this is very long time. Okay, so this value is very long time, which time this 100 micro seconds. Okay, now to move on next. So here the graph which is shows illustration, just you have to watch through this. What is the observations from this graph? On x-axis you can see the ratio of the electric field strength over the pressure, which is watt per meter atm, and on y-axis you can see a relationship of the drift velocity, and the ratio is about 10 raised to power 5 meter per second of the drift velocity. And this graph is basically telling us about the electron drift velocity as a function of electric field divided by the gas pressure. So relationship between the drift velocity and the electric field divided by the pressure is mentioned in this graph. Two gases which we are taking. The first gas is we are taking the methane, and the other gas we are taking a mixture of argon plus 10% of methane. So what we are observing from this graph, the peak of only methane gas, in that the drift velocity is increased because the mixture of only one gas, methane. But as there is a mixture of two gases, argon plus methane, you can see as you increase the electric field per pressure, means as you increase the electric field, definitely the pressure has to be decreased. So by increasing the E by P ratio, what you can observe for argon plus methane gas, the drift velocity goes decrease. Okay, so when a mixture of gases has to be involved, then the ratio of E by P should be decreased, means the drift velocity decreases. Okay, as you increase the E by P ratio. But as you increase the E by P ratio of a gas, of a single gas, monogas, you can say like methane in this curve, you can see the drift velocity has to be increased a sufficient value and it remains constant up to as it reached the value 1 meter. Okay, so this illustration we get from this graph. So our final topic of today's lecture, which is the ionization current. So what is ionization current? So in the presence of an electric field, we know that what is ionized, because when a charged particle is coming has to be interact with the ionized chamber having gas inside. They produce ion pairs either by excitation or ionization, two factors either by recombination or other processes. The ionization current has to be performed because you are applying now external electric field. So as you are applying the external electric field, the inside molecules have of that gas has to move. They not stay on a single position. They have to be moved from their original path, from origin to somehow they fluctuate. They're not gonna remain rest. They has to be moved. As your charge particle moves, you know that moving charges produces current. So as the charges move, so there is a production of current. Yes, you are right. So in the presence of electric field, the drift of the positive and the negative charges represented by the ions and the electrons constitute an electric current. So those ion pairs which are having drift velocity after the charge particle interaction with that inner with the gas inside, and gas produces the ion pairs, and that ion pairs after the deflection by the external electric field, they gain drift velocity, and due to that drift velocity for the positive and negative charge ions, they constitute electric current. Here it is mentioned. So if a given volume of gas is undergo a steady state irradiation, the rate of the formation of the ion pair is constant. Okay, so if a given volume of gas is undergoing a steady state of irradiation, then the rate of the formation of production of the ion pair which has to be produced is constant. Okay, so for a very small test volume, you can say, of the gas, this rate of formation will be exactly balanced by the rate at which the ion pairs are lost. Okay, from the volume either through recombination or by diffusion or migration from the volume. Okay, under these conditions the recombination is negligible in that scenario, and all the charges are efficiently collected, and the steady state current produced in an accurate measure of the rate at which your ion pair are formed within the volume. So this is how you can define the steady state current. The steady state current produced in an accurate measure of the rate at which your ion pair has to be formed. So in which volume, within the volume means within the chamber, the ion pair which where they has to be produced, they produced a steady current. So measurement of this ionization current is based, this is basically ionization current. This is not due to the excitation. Okay, so the ions that are formed, they produces the ionization current, and this steady current formed is called as basically the ionization current, because this is due to the ionized particles, ion formed particles, not due to the excitation particles. The excitation which we discussed, that they move to the higher energy state if they have no sufficient amount of energy. In that scenario, no current form, only the current formed after the an ion pairs has to be formed. Okay. So figure 5.3, we can discuss this figure below. Illustrate the basic elements of the rudimentary ion chamber. A volume of gas is enclosed. You can see a volume of gas which is enclosed within a region in which an electric field has to be applied. You can see we are applying an external electric field Here is negative, here is positive. External battery source, electric field we have to be apply, and you can say there is a volume inside. These are the gas molecules, and we have two plates, we have two electrode plates. So what we are going to do there, a volume of gas enclosed within a region in which an electric field can be created by an application of an external voltage at equilibrium. Okay, at general cases, the current flowing in the external circuit will be equal to the ionization current. What is ionization current? Means the number of ions produced in this is at equilibrium. The number of ions produced inside those gas filled chamber is equals to the external circuit. Okay, external circuit this. In this scenario, the current flowing or in this gas molecule, which is the current which is produced after the ion pairs produced, which is the ionization current. So ionization current must be equals to the this external current, okay, collected at the electrode. So ionization current has to be collected at electrode, and this balances the external circuit current. Okay, now this is in equilibrium condition. And sensitive ammeter placed by an external current and therefore measured by the ionization. So we can measure the current easily by just installing an external ammeter to this circuit, because you know that ammeter is a device which is used to measure the current. Okay. So the graph we observed, the graph relation between the current I and V. This is the IV curve. Okay, the basic components of the ion chamber and corresponding to the current voltage characterization. So you can see this small peak and this large peak we are getting. So small peak is basically for the low irradiation rate, understood, and this large peak we are getting, and this is for the high irradiation rate, understood. So this is how we can conclude that ionization current must have to be produced once your charge ion pairs produced. Means steady state current has to be produced when your ion pairs have to be formed within the volume, not outside the volume. Within the volume, current has to be produced. So we can detect that current by this experiment by just installing an external ammeter and an external voltage. We can easily measure that current. If this voltage compares this external internal voltage of this ionization current, then we can easily measure the values. So provided recommendation is negligible, it should be noted that the saturated current does not change if the ionization electron remains as free electrons during gas drift. And so it's saying that if your electrons remain electrons after the ionization, after the basically saturation current, or you can say after the ionization of electrons, if your electrons remain free electrons, and then there is no drift, so there is basically the recombination is negligible. Okay, so and if the attachment occurs, the drift velocity is now thousands of times lower, but the equilibrium concentration of the negative charge will then be higher by the same factor, since current depends upon the product of the charge density. Okay, so on which factor the current has to be depend upon? So the current basically depends upon the product of the charge density, means the number of charges in a unit volume, which is the charge density, and the drift velocity. So on these two factors your current has to be depend. The more the charge density, the more the current formed. The more the drift velocity of the uh, uh, pair ions inside the gas chamber, the more the current they produce, because because the ions which having the greater drift velocity, they can produce more current, because more drift velocity means they are more thermal in motion. So as they are more in thermal motion, they vibrate more, they more fluctuate, and due to that fluctuation the charge particle move, and due to the movement of the charges they produce more current. So this is the concept behind the production of the current means the ionization current, which is formed when a charged particle is coming inside the ionization chamber, which having the gas inside, and they have to be produced these ion pairs, and ion pairs, if they are not in rest, they have to be moved, and if they move with a faster speed, they gain the drift velocity. By gaining the amount of drift velocity, they produce the current, and we can current observe that current with this experiment. So that's all for today for this lecture number 16 of principal methods and applications of nuclear tracks. In coming lecture, we can discuss more interesting about this course. So in this lecture, we discuss chapter number 7 of the book Gallon F. Canol, which is the radiation detector, and the chapter is chapter number 5, which is about the ionization chamber. We discuss these factors today. In coming lecture, we will continue our chapter number 5, okay, from here. Okay, so till then, take care. Allah Hafiz.